by way of introduction, I think we all know that astrophysics is still an observational science. We don't really have the ability to calculate ab initio the evolution of objects in the universe, but neither are we able to do that for the very smallest objects, which are the molecules, which are the subject of today's talk. And I'm extremely glad to be able to introduce our speaker, Holger Kreckel, who has, for the past years, been working in a very special environment in the Max Planck Institute for Nuclear Physics in Heidelberg, where there exists this machine called the Cryogenic Storage Ring, which can simulate the conditions of interstellar space effectively in the laboratory. Now, Holger has been working with this with his team as leader of the molecular astrophysics group at the Max Planck Institute. Holger did his PhD starting way back at the beginning of the century with Andreas Wolf at the Max Planck Institute for Kernphysik, and he did a postdoc there for 2 or 3 years, also with Dirk Schwalm, before moving to the United States, where he was postdoctoral research at Columbia University, working with Daniel Savian. And that was followed 2009 by a position as research scientists working with Ben McCall at the chemistry department in the University of Illinois. And at that point, after that postdoctoral appointment, Holger was awarded an ERC starting grant, which he used to come back to Heidelberg, to the Max Planck Institute, where he moved forward on this whole topic of laboratory astrophysics, starting with what was the warm storage ring, which became the cold storage ring. And it is my extreme pleasure to be able to introduce Holger. Please tell us all about molecular astrophysics at the Cryogenic Storage Ring. Thank you very much.
All right, I hope I can be heard. Thank you very much, Richard, for this very nice introduction. First, I need to get all the technology right. Okay, I suppose you can all hear me. Also, the internet can hear me. All right, so thank you very much for having me here. I feel especially honored because I'm not an astronomer to be invited to this colloquium here, but I do see a number of familiar faces, though I don't feel like a complete alien here. And today I will talk about the research we do. This thing doesn't fall down. The research we do at the other Max Planck Institute, at the Max Planck Institute for Nuclear Physics in Heidelberg. That's halfway up the hill, not all the way at the top. And as Richard says, we care about molecules. We care about molecules in interstellar space, how they get formed and how they get destroyed. So let's start. You've probably seen this picture many times. This shows different phases and different objects in interstellar space. And in most of these objects, we have discovered molecules in the meantime. There are about 240 different molecular species that have been detected, and they play an important role in all of these environments. And they range in size from simple diatomics like H2 all the way up to fullerenes. And the question of how these molecules form and what kind of molecules are out there are also connected to questions that are very important on our own planet, like the origin of our own water and the possible delivery of organic molecules from space. Now, a number of the major investments that the astronomical community has done in the last years were geared towards understanding molecules, and were particularly good in the far infrared and millimeter part, like the Herschel Space Telescope and ALMA. And of course, also JWST has capabilities in the mid-infrared that are particularly good to image certain molecules. Now, the fact that the interstellar space has places where it's almost fully molecular, that didn't come natural to the scientific community. In fact, while people have been gazing at stars for centuries, up until not so long ago, it was believed that the space between the stars is mainly empty, and if at all, then filled with a little bit of atoms, but no molecules, This here is a lecture from Arthur Eddington that he gave, the Beckerian lecture that he gave about 100 years ago at the Royal Society, where he said that it's difficult to admit the existence of molecules in interstellar space because once a molecule becomes dissociated, there seems no chance of the atoms joining up again. Now, I know that it's enormously unfair to take such a statement out of context and confront it with reality 100 years later, but I'm still going to do it. Because today we know that there are places in space that are full of molecules, actually, and we have discovered about 250 of them. But it's still true that astrochemistry or molecular astrophysics is a rather new subject, because even after the first detections came in interstellar space, in the 1930s and 40s, here we found something like CH and CN. These are all very strange molecules. These are radicals that you wouldn't find here on terrestrial environments. And then the third molecule that was found was CH+, that's molecular ion, and that you only get in like discharges or so. You need to have a very violent process to produce this. So these didn't really change our perception of interstellar space because those were considered as oddities, weird molecules that formed under very strange conditions. That only changed in the late 60s or so. And that was kind of a missed opportunity because in actuality, if you look at the second molecule that was detected, this cyanide radical here, that has a very large dipole moment. And if you look at the observation, this is the original photographic plate from 1940 or so, there were 2 lines detected. And from 2 lines, you can infer a rotational temperature. And that rotational temperature was 2.3 Kelvin. And at the time, people didn't know what to make of such a low temperature. So Gerhard Herzberg himself, he famously put that in his textbook that this probably has a very restricted meaning. So he completely dismissed it. When in fact, they were looking at the first measurement of the cosmic microwave background temperature. And in the 90s, you can actually show that with CN, you can measure it to 3 or 4 significant digits, almost as accurately as with the COBE satellite. Nevertheless, that wasn't realized at the time. And the perception of interstellar space as a more fruitful place for chemistry only changed in the late 60s when radio astronomy came around about the time when Charles Townes moved to Berkeley, and he announced that he wanted to look for more complex molecules in space. And that was considered by his colleagues as kind of a wild idea. But then again, he had just gotten the Nobel Prize for developing the maser and the laser, so he was granted some liberty to do some extravagant stuff. So he had his students build some receivers for ammonia and water, and they put it on a telescope and found it immediately. It was very simple, actually. And that's when everything changed, because that was at the late 60s, and people realized that these kind of molecules, those cannot be formed in a super dilute environment that is just cold. They have to be processes at work. They have to be denser regions in space. And this is when astrochemistry really took off. And then in the early 70s, people started to think about what kind of processes could make molecules like that in interstellar space. And it turned out that the key were reactions of charged particles. So what you see here is this tree of ion-neutral reactions, because what happens if you ionize hydrogen, because interstellar space has an abundance of hydrogen, it reacts with another hydrogen, it will form this notorious H3+ molecule. Triatomic hydrogen, that is a molecule that I spend a lot of time with, and it has very special properties. It's very stable. It's almost impossible to destroy it with radiation, so it will survive on its own in interstellar space essentially forever. But on the other hand, it's also very reactive. Okay, we're back. So this molecule basically likes to donate its extra proton to anything that comes by, to like different atoms or other molecules, and it starts this reaction change that builds larger and larger molecules by ion-neutral reactions, all the way up to organic molecules or something like protonated water. But because we're talking about positively charged particles, they're constantly at the risk of meeting a free electron. And if that happens, they will dissociate and neutral particles and molecules will be released into the interstellar medium. And today we believe that, at least for the smaller molecules, this competition between ion-neutral reactions that make larger and larger molecules and this electron recombination that terminates those reaction chains, that is what determines the abundances, at least of the smaller molecules in interstellar space. Now, you can ask yourself, how did we, as an Institute for Nuclear Physics, get roped into this kind of research? And the answer comes when you look into the different reactions you have to consider in an interstellar model of a molecular cloud or something like this. Don't try to read all of these processes. This is a statistics from a database from about 10 years ago, where you can see the different processes that are relevant in interstellar space. And in total, there are about 4,500 reactions. And if you take all the reactions that involve charged particles, it's about 80% of them, more than 3,500. And there's one particular reaction, this one here, this is the electron recombination that I just mentioned before, that was very difficult to measure at the time, but it's very important because it determines the ionization balance, and it also determines which particles form the branching fractures and actually get formed in interstellar space. So this was very difficult to measure. And it turned out that at our institute, we had a machine that was very good at measuring that, but we didn't even know that, you know? And now we come to the real topic. Now I realize that we're having the astronomical colloquium here, and this is not a telescope, but I'm gonna approach the subject with great caution, and we're gonna take only what we need to go forward. So all of you have probably heard of heavy ion storage rings in the context of these high energy physics institutes of CERN or other institutes working at very high energies, like the Large Hadron Collider here, the LHC, which is about 27 kilometers in circumference, probably the largest experiment on Earth. So this is technically a heavy ion storage ring, because in my book, anything that can store anything that's heavier than an electron on a revolving orbit is a heavy ion storage ring. But the kind of storage rings I want to talk about today, they look different, but they all work on the same principle. You know, you need two different ingredients. One of them is an ultra high vacuum pipe. That's what you see here. Vacuum is very important in our business. And the other thing is you need a force to keep the charged particles on their revolving orbit. And the force to use is the Lorentz force. And you can see if you just apply a homogeneous field, we all know that can force a particle at a certain velocity on a revolving orbit. And that's useful. Therefore, almost all of these storage rings use the magnetic part of the Lorentz force. There's another reason. If you put in numbers here, you know, the Lorentz force scales with the velocity and the B field. And if you take the magnetic field of a normal electromagnet, like 1 Tesla that you can build in the lab, and you go to high energy physics, all the particles travel essentially with the speed of light. And then you get a very strong force. If you compare that with the electrostatic force here, you would have to do something like millions of volts per meter in order to match that force. And therefore, the magnetic field is typically much better at high energies. But on the other hand, it also maxes out because you cannot go faster than the speed of light. And there's a certain strength of magnetic field that you cannot exceed. And that's why 20 kilometers of the LHC are full of superconducting magnets at 8 Tesla. And it's much harder to go faster. So for now, let's just say if you go to the CERN accelerator school and you tell them you want to build a storage ring purely with electrostatic fields, they will laugh at you and send you home. So most of the storage rings will be built with magnetic fields, but let's keep in mind that this part here exists, the electrostatic part. So besides these these collider rings have a very specific purpose, right? They want to make particles, accelerate them to a speed where you can see high energy physics effects, you know, to the highest possible speeds. But there are different storage rings that were also pioneered at CERN. And this was the first one. This is the low energy antiproton ring. It looks quite different. It's much smaller, about 100 meters in size, and it has a different purpose. It's a cooler ring. That means the idea is to take the beam and make it better, make it more brilliant, and provide it for different experiments, you know? And when this thing ran very successfully in the 80s and 90s, it kind of coincided with the time where ultra high vacuum technology became manageable for smaller labs, not only CERN. And then all around the world, these storage rings were being built. This here is a historic slide that you can find on the CERN webpage. So this is, you can see storage ring came in different shapes and sizes all over the world, in America and Japan, here in Europe. And the first one that was built after Lear was this one here, the TSR, or test storage ring. And that was built here in Heidelberg. It was called test storage ring because people really didn't know whether it would work. And then it ran for about 25 years and the name never got changed. And this is where I grew up, so to speak, scientifically, around this machine. There were different ones in similar size, about 50 meters in circumference, and they would work at moderately high energies of mega electron volts, you know? Now, why is such a machine useful if you want to study molecular reactions in space? Let me try to show that to you. So let's say you want to study the reaction of this iconic H3 plus molecule with an electron. That's very important for the ionization balance in interstellar space. What we would do is we would produce these molecules in an ion source, then we would accelerate them in a particle accelerator to a few % of the speed of light and inject them into the storage ring. So in reality, they would fly around a few 100,000 times per second in there, and they could cool down. And then we would switch on a very monoenergetic electron beam in this device here, the electron target, and the electrons would fly at the same velocity as the ions, and the ions could capture a free electron, and then they would dissociate, and we can measure the fragments one by one, the neutral fragments. So that turned out, while these machines were not built for such a reaction, that turned out to be an extremely powerful technique. And the reason is that you have, at these energies, you have 100% detection efficiency, so you don't miss a single particle. And you get very high resolution for these reactions, and it allows the ions to cool down. They come out of a hot ion source where they have been ionized, they're vibrating and rotating, and they get some time to cool down because we're in a storage device. Now, let me try to explain to you why you get such a high resolution The secret is this formula. I think it's the only formula that I show. And it's essentially just a frame transformation. If you take two beams at energies E1 and E2, and you superimpose them at a certain angle, if you make that angle such that they're collinear, then cosine theta is 1. And if you make E over M the same for both beams, then the whole bracket cancels out, which makes sense. If you have two collinear beams traveling at the same velocity, the internal relative collision energy is 0, you know? And that for us turned out to be very useful, because if you take an H3 plus beam at about 5 mega electron volt, which is, oh, my pointer is gone. Oh, there we go. If you take about 5 mega electron volt H3 plus, to have the electrons at the same velocity, they have to have about 1 kilovolt. And that is very nice, because then you can tune them by just changing in your lab power supply by 1 volt, and you can tune the energy of collision very, very precisely. If you try to, you know, collide an electron at milli-electron volt, a very low energy with a resting target, that's almost impossible, because already the contact potential between different materials have volts. So the electrons will go anywhere, but not where you want them to be. You know? So this turned out to be very useful, and it allowed us to do measurements like this here. So this here is this famous reaction, H3 plus electrons, where you see it breaks up into neutral fragments. Well, it really doesn't seem to. Ah, there we go. I think the computer is slowing down. Okay, maybe this doesn't work anymore. So we have this reaction of H3 plus with electrons, and you can see that we can measure the rate coefficient for this reaction, which is probably one of the most important reactions in interstellar space, over orders of magnitude in the rate coefficient, and also over orders of magnitude in the collision energy here. And you can see we have two different measurements here, one of them here in Heidelberg and the other one in Stockholm, which agreed over orders of magnitude. Before, because this was such an important reaction, there were about 30 or 40 published values for this rate coefficient that disagreed by 4 orders of magnitude, you know. And with this measurement, we kind of pacified the whole discussion, and it was finally clear what was happening. And the reason was that the other measurements didn't measure the entire energy scale. They measured one point somewhere, you know, at certain energies. The other important thing is that the resolution is quite good. That means here at 1 milli-electron volt, where our transverse resolution ends, that is, if you convert it to a thermal energy, that's about 10 Kelvin, you know. And that means that we can go down to 10 Kelvin. We can also go down to up to 10,000 Kelvin. We can cover whatever energy we need. Okay, so let me just remind you a little bit about very fundamental molecular physics, because I know in our curriculum it sometimes gets omitted. So molecules, in contrast to atoms, can vibrate and they can rotate. You know, we know that. And with molecular vibration, we usually associate with something like a spring movement. And that, because we're physicists, we have to reduce to something we understand, and we use the harmonic oscillator approximation. So we say the harmonic oscillator has these, I think I'm going to switch to a normal laser pointer because this doesn't seem to work anymore. Yeah, I'm sorry, I'm going to take out a normal pointer. I think the computer is just slowing down or something. Sorry to the online audience, but our technology is failing. So I'm going to need this double machinery now. Okay, so we're talking about the harmonic oscillator approximation. That means we have just equidistant spacing, and those equidistant spacing for small molecules, they depend on the vibrational band energy, and for a small molecule, that's thousands of Kelvin. That means if you get your molecule or your molecular ion in equilibrium with a room temperature environment, those go away. You know, the vibrations are relatively harmless. For small molecules, the frequency scales with the inverse square root of the mass. For larger molecules, that's no longer true. And the rotations, we also approximate with something, because we're usually bad at understanding more than one dimension. We go into the rigid rotor approximation, where we have a rotational constant. And the rotational constant is essentially the inverse of the moment of inertia. And again, that means small molecules have large rotational constant and vice versa, you know. And for a small molecular ion, this rotational constant, a large rotational constant, would be on the order of 50 Kelvin or so. That means at room temperature, even for those small molecules, you still have between 5 to 10 rotations still present whenever you are, even in equilibrium. And that turned out to be a problem. So in many experiments at the TSR, we actually found out that these vibrations for those molecules that are not too symmetric are, with the words of Douglas Adams, mostly harmless, while the other ones are actually rather problematic, because those are around, and we could also show that they matter, you know, that they change the reaction rate coefficient. So we had to fight these ones. And our approach to that is a new storage ring that's called the cryogenic storage ring. And that's quite a different machine. It's a little bit smaller than the old one, about 35 meters in circumference. And you can see already it doesn't have magnets anymore. So what it has is these outer cryostat chambers here and an inner ultra-high vacuum chamber. And now the deflection is no longer done by magnets. So now on the outside, the deflection is done by electrostatic plates that are inside the vacuum. So essentially we have high voltage plates inside the vacuum chambers. If we put to 20, 25 kilovolts, then the particles get deflected by the electrostatic force. Now the advantage of that is, as you can see here, that the force, the part of the Lorentz force, does not depend on the velocity anymore. It only depends on the kinetic energy. That means if we shoot in a proton or a biomolecule, they all fly on exactly the same trajectory. So this is really a machine that is geared towards molecular ions, because the magnetic storage rings were their limit with heavier molecules because they're always singly charged. The Q you can't get up, and they're slow. And then deflection doesn't work. Here, it doesn't matter anymore. So the other thing that we have is that the whole storage ring is cryogenic. So these inner chambers here are cooled by a liquid helium circuit to temperatures below 10 Kelvin. And that has two reasons. First of all, we want to get the molecules cold, like in interstellar space. And the other one is, since we're working at lower energies now, the lifetimes of the beams, they get adversely affected by that low velocity because the capture cross sections go up. So we were aiming at a vacuum that is about another 2 to 3 orders of magnitude better than what CERN or what the other storage ring had in their machines. And we didn't really know whether that would work. Then we wanted to build a rather versatile machine, so it can store positive and negative ions. And we wanted to have these merged beams experiments again, because those proved to be so useful. And we wanted to have electron cooling again. And that was a big challenge, because now we are at smaller velocities. We had to make a slow electron beam. Okay, so this is what the machine looked like in 2015 before it was closed. And you can already see that conceptually, although it's a little bit smaller, it's actually much more complicated than the magnetic storage rings, because now everything is on the inside. And the whole structure has to take temperatures from 4 Kelvin all the way up to 500 Kelvin when we want to get the water vapor out. Then we bake the whole machine and we cool it down. So from an engineering point of view, that is much more complicated. The inner chambers here look like they're made out of copper, but they're not. They're made out of a special stainless steel. But stainless steel is such a bad heat conductor that it would have taken too long to cool it down. Therefore, everything is clad in copper. The electrodes that keep the particles on their orbit are inside the chambers, and the whole storage ring, of course, shrinks when we cool it down, but those have to stay in place relative to one another to better than a fraction of a millimeter. So that had to be solved. So from an engineering point of view, this is much more complicated, but I don't want to bore you with the engineering parts. So I'm going to go to the first milestones. I'm going to just rush you through what we found out in the first couple of experiments we did there. So we started to switch on the helium refrigerator in March, I think, 2016. And then it took about 3 weeks till all the chambers had reached 5 Kelvin. And that's typically what we do. We bake the machine for 2 weeks, and then we cool it down for about a month. And then we keep it cold for a couple of weeks. Then we began to inject ions. And here we used one of those ions, like a silver dimer, a heavy ion that's singly charged, because we wanted to prove that this we can do. And you can see we can store it for about 5 to 6 hours. And you can see it, there's almost no background. And such an ion in a magnetic storage ring would have lived for maybe a fraction of a second or something like this. We also can store a lot of ions, and you can see them by their mirror charge. This is a bunched beam where you can see that we store about 2 to the 8 particles. We can go up to 2 to the 9 if we really have to. And from this, we can infer what kind of vacuum we have inside our machine. You cannot really measure that anymore because we're essentially talking about individual particles. There is no pressure measurement that can do that. We can infer this value from the lifetime of the beam and from estimated cross sections. And we ended up with a value of about 100 particles per cubic centimeter, which is relatively close to the diffuse interstellar medium or something like this. So this exceeded our expectation. And now we were ready to store particles, but we also wanted to show that the molecules that we keep inside there really reach their lowest quantum states, that they reach the same states that we see in interstellar space. So we picked a rather iconic ion, this CH+ ion, the first ion that was detected in interstellar space. So please don't try to read this text. This is the whole publication, actually, of the detection of the first molecular ion in space, And we used this ion. CH+ is very special because it was the first one that was detected in space, and we still have no idea why there is so much of it. It's still completely not understood how it forms and why it doesn't get destroyed more quickly. So we took a reaction of CH+ with UV photons. So what you see here are the potential curves of CH+. There is a singlet sigma state, the ground state. And if you hit the molecule with a UV photon, you can actually lift it above this dissociation level here. You will couple only exclusively to this upper singlet pi state with dipole radiation. But the funny thing about CH plus is that the outgoing channels, there's two different possible outgoing channels. One of them is the upper fine structure level of carbon plus, and the other one is a lower fine structure level. And for those of you who work in ISM physics, you might know that this is a very prominent interstellar cooling line between here. So if you lift some of the flux just above the dissociation limit, it actually can't go out until it breaks the symmetry and couples to the lower state. And this leads to resonances because you have a bound state in the continuum. And so you have a window of resonances of 64 inverse centimeters that you can reach. And depending on which rotational state you start from, you need a different laser energy to go into that window of resonances. So this we wanted to use as a thermometer for CH+. So here you can see some of the measurements. So what you see here is a photodissociation signal as a function of the laser wavelengths. But you can see there are some wiggles in the signal here. And these wiggles we can actually understand in all details. We can assign them. So this part here belongs to j equals 2. Then here is j equals 2, and j equals 0 would be around here. And the reason that we're already at these low rotational states is that we already waited from 5 to 25 seconds. So all the higher states, starting at thousands of Kelvin, they have lifetimes of microseconds to milliseconds. They're already gone. And we're now at the lowest states already. And then we can go to something like 50 seconds. Now j equals 1 comes up. We can go to 80 seconds. We can go to 2 minutes. Now j equals 0 comes in. We can go to 3 minutes, to 4 minutes. Now j equals 0 is dominant. And then we stopped. We could have stored the ions longer, but the problem is that the UV light was very harsh on our cryogenic detectors. So we stopped there because we had enough information for what we wanted to understand. And from just looking at these abundances as a function of time, you can model the decay. The only thing you have to know is the dipole moment of the molecule and the rotational constant, and all of that you can find in tables. And then you can model the decay. And it doesn't matter at all if you start at 1,000 Kelvin or at 5,000 Kelvin, because all of the higher states are so short-lived that the decay is dominated by these low J states. And what we found is that the decay is consistent with an effective radiation field on the order of 15 to 20 Kelvin. So this is higher than the temperature of our walls in the storage ring, but this was to be expected because we have some few ports for the lasers, so there is some blackbody radiation leaking in. We repeated the same kind of experiment with a negative ion, OH minus, which is much easier because the cross-section to detach an electron from a negative ion are 3 to 4 orders of magnitude larger. And also you don't have to work in the UV. And we found that we have about 15 Kelvin effective temperature, and we got 92% if we waited longer and got it into equilibrium. Okay, so now we have a machine where we can store molecular ions. We can store them for a long time, and we can wait until they really reach their lowest quantum states. And then what we had to do is, that was around 2017, we basically tore half of the storage ring apart again to actually put in the experimental stations. And there were two main experiments put in. One of them is another electron cooler, and this was, the work of Andreas Wolf and Olga Novotny. This was put into this section here. And then this section here, so this was again to study electron collisions and recombination. And in this section here, we put in another newer gadget to study collisions of neutral atoms. And this is what my group did. Okay, let's start with the electron cooler. So the electron cooler looks like this. This is really the masterpiece of Andreas Wolf because it's really, really hard to build an electron cooler for such low energies. So he pulled all the stops. What is done here is that this is a part of the storage ring. This here is a stored ion beam in red, and the electron beam is in blue. And the electron beam starts here, and it's actually not coming out of a normal thermal cathode like a glow bulb or something like that. It's coming out of a surface, and the photo effect is used. And the electrons are produced inside a superconducting magnet and then slowly expanded so that they cool down. Then they're transported at about 20 eV into the storage ring. They're merged with the orbit of the storage ring. And here they can be slowed down to 1 electron volt while maintaining that low internal energy of 1 millielectron volt. This is really a masterpiece. I believe it's probably the best defined and well-controlled electron beam in the world. And let's now assume, again, I don't want to bore you with the technical details. Let's assume this works. What can we do with it? Well, it's always good to start with the first things, and first things for molecules would be the early universe. And the early universe is a nice place because it's much simpler than today's universe. You have to deal only with hydrogen and helium. We have about 20 to 30 reactions. Today we have maybe 100,000 reactions to deal with. So if we start in the early universe, before the recombination happened here, actually we had already the first molecules. And the first molecules are crucial because they help to form the first stars at about 400 million years later. And the very first molecule that was formed in interstellar space, we believe, is helium H+. And if you followed the popular science news about 3 years ago, you might have read that helium H+ was actually found in interstellar space, and it was found by this flying telescope here, you know. But it was found in a planetary nebula, which probably all of you know is not exactly the early universe, but it's more like a star that is no longer a star. The question that we have now is, can we maybe actually detect it in an object that's closer to the early universe? And for this, we have to understand how much there is. So we have to understand the formation and destruction mechanisms. So in the early universe, this here is a plot of the abundances. It's a plot that has a lot of, tick marks per 5 orders of magnitude per tick mark. And here you can see the molecules that you can form in interstellar space. And if you have only hydrogen and helium, you can only form hydrogen and helium molecules. And helium H+ is the first one because helium has such a high ionization potential, of 24 eV, so it will get neutralized first. And then you can form helium H+, and that happens already at redshifts, of a few hundred or a few million years, or even thousand years actually after the Big Bang. And the formation mechanism is this one here. It's believed to be fairly well understood. That's a radiative process where helium, because it's the first neutral atom, meets a proton and then radiatively recombines. The destruction happens through two different processes. Helium H+ can meet with a hydrogen atom or with an electron. And this is the one that is actually relevant at later stages, around about here, about 400 million years later or so, when the first stars are being formed. And helium H+ is interesting because it has a large dipole moment. And despite the fact that it has a relatively low abundance compared with H2, by orders of magnitude lower, H2 doesn't have a dipole moment. So as a coolant, it's still interesting. And HD has a very small dipole moment, so helium H+ might play a role just because it can cool much better. So because this reaction is important, it had been measured before, twice actually, at a storage ring in Japan and a storage ring in Stockholm. And you can see the measurements agreed quite well. And both of these were room temperature machines. When Holger and his team measured them at the CSR, you can see it looked quite different. It's about an order of magnitude lower at low energies, and then this monstrous resonance shows up at somewhat higher energies. And the reason for that is that we're now in the lowest quantum states, like in interstellar space. This is such a large dipole moment that 10 seconds after storage, already 85% in J equals 0. Now, the interesting part is, because we can predict now how it cools, because we know the dipole moment, we know the rotational constant, we can not only predict the cross-section for J equals 0, but also for J equals 1, 2, and so forth. So we have now state-selected cross-section, and that's a new quality of data, because in interstellar space, we're never really in thermal equilibrium, right? The gas kinetic temperature is different than the radiative temperature, but if you have state-selected cross-sections, you can convolve them with whatever you need. And if you do that, you can basically go down to a rotational temperature of the cosmic microwave background. You can assume the gas kinetic temperature, or even go higher. But whatever we do, our cross-section, because it's so much lower at low energies, is much lower than what was used in cosmological models so far. And that means that the predictions of how much helium H+ there is in the early universe are probably wrong, starting at redshifts of about 10 or so, because then the electron recombination becomes dominant, and we believe that there should be about a factor of 20 more helium H+ in the early universe. Now I find that particularly interesting because now that JWST is flying, one of the mission statements was to see the first light in the universe. So it's a good idea to understand these handful of reactions that we really need in detail. Okay, so this was helium H+. Now we work our way up to those species with a significant abundance that are a little heavier. So this here is a work of Daniel Paul of the CH+ electron recombination state selectively. This actually got published yesterday, if you're interested in that. And so what we see here is, again, the electron recombination cross-section. So how likely is it that an electron destroys this molecule? But there's another process that can happen. The electron can approach the molecule that's rotating, and then it can slow down the molecule and leave again. This seems unlikely at first, but it actually happens. And this has been used and calculated in models of interstellar space, but it never been observed in the wild, So there were cross-sections, and they're purely based on theory. But now that we have the electron cooler, and at the same time we have this laser diagnostics, we can actually see that the rotational cooling is much faster if we have the electrons on at the same time. Well, this is actually a very complicated measurement because you have to disentangle the cooling effects of the electron from the depletion of the electron, from the radiative effect, from the effect of the laser and all of that. So that was a very complicated measurement. But Abel Kalosi, who led that work, disentangled that. And then we can present the first ever inelastic electron cooling rates for a molecular ion that can be compared to the calculations in interstellar space. Now moving forward, going to a somewhat heavier species. Again, this is from Abel Carlosi. This is OH+. So now we've done a measurement of this one here. That there were also previous data that ended here, and you can see they missed this resonance coming in here. And I found OH+ particularly interesting again, because when Herschel was flying, one of the Herschel missions was to detect water in star-forming regions. And it detected a lot of water, but I believe actually not as much in many environments as they were hoping for. But what it found was OH+, H2O+, so all the precursor ions, which were not supposed to have been there. And these ions were then used to infer important parameters for the sidelines, like the cosmic ray ionization rate and the molecular fraction. But the rate coefficients that were used for those analyses, they were really inadequate from my point of view. Some of them were derived from the dirt, from the water vapor that people had in their machine in the 80s, So you have $1 billion instrument and the rate coefficient are completely inadequate. So I hope that we can actually change that situation and go through this gas phase formation chain of water and look at all of these reactions and put them on a better footing. We have started already. We have measured the reactions of OH+ with H2. We have measured the reaction of H2O+ with H2. That's a different type of measurement that a postdoc of mine, Sunil Kumar, did in a different setup. And now we have the OH+ rate coefficient, and we hope that in the near future we can do the protonated water and we can do the water molecule itself. And then we can also eventually do this reaction here, which is H3+ plus oxygen, for which we need neutral atoms at collision partners. Now, I should say that most of the water in many environments is actually not created in the gas phase, but on surfaces. But nevertheless, the observations are done in the gas phase. So we still need to understand the gas phase reactions. Okay, another thing that we did recently, and that is due to our Lord of the Rings, Manfred Grieser, is that we figured out a technique to look for impurities inside our beams. Because if you, let's say, where do we want to take this? If you want to go to heavier and more complex molecules, then you have to understand what you have in your beam. And this here is a picture of an OH+ beam where you can actually see the contaminations overtaking, getting separated from the beam. It's kind of a time of flight measurement. And you can see that we have a little bit of ammonia in there, and this we can use now to go to more complex molecules to separate, for example, which used to be very difficult, H2D+ from D2+ and make a pure H2D+ beam. They have the same mass, they're molecular isobars, but the resolution is good enough to separate them. And then we can go to these molecules. So this would be deuterated H3+. But the next problem is if you go from a diatomic to a triatomic, the complexity increases enormously. Now we don't have a handful of states. With some transitions, we have about 5,000 states connected by 50 million transitions. But we can lose the exomole line list. Those of you who work in exoplanets might know that. And we can solve these coupled equations and predict how this would cool inside a cryogenic environment. And this was done by Aiga Snotins, one of my students. And we can actually see that if we store the particles long enough in the storage ring, we will reach only 3 states eventually, after about 1,000 seconds in a cryogenic environment. And that's similar to what we have in interstellar space. And if you look at the rate coefficient, what happens? So if you go from a short storage time of 4 seconds to about 1,000 seconds, you see that here in this region, it changes, the rest stays the same. But this is the region that matters. And if you zoom in, so we're talking about 1 milli-electron volt, so maybe 10 Kelvin, to 1 eVolt, about 10,000 Kelvin. And you can see that these structures show up. And we try to understand those. These are individual state populations, essentially. Okay, so where do we want to take this in the future? About a couple of years ago, Eric Herbst was visiting Heidelberg, and at the time already he was talking about these organic molecules that were found in environments in interstellar space where they really shouldn't be. And his conclusion was that there has to be gas phase processes that we don't understand yet. And this has culminated very recently in the first detection of PAHs, real polycyclic aromatic hydrocarbons, these cyanonaphthalenes that were found in TMC1, and it's completely unclear how they get there. If you look at the models that people can make, so these are the observations here, the abundances, and the solid lines are the models. They're between 4 and 6 orders of magnitude too low. And the question is, how can we solve this? Now, in the models, they try to just inject a whole bunch of naphthalene without knowing where it would come from. Then they come close to 2 to 4 orders of magnitude, but it still does not work. And a similar case was actually a couple of years ago in methanol. Methanol was kind of used as a poster child that you cannot form a large organic molecule in the gas phase because the way from protonated methanol, if you have a methanol with an extra proton, when it recombines to an electron, that was measured at another storage ring. But you see, it gets immensely complex. You have these different channels that open, and the one that you're interested in is the one where the methanol stays whole. And in the measurement, they found that it's 3% plus minus 2%. And that was interpreted as 0. And from that time on, basically, all the astronomical models said we cannot form organic molecules in the gas phase. But now it seems like the pendulum is swinging back because they cannot produce these molecules in the models. And in this PAH study, they suggested it's electron recombination of protonated naphthalene that's responsible. So how can we measure something like this? This is, of course, a much more complicated system, and our current detectors wouldn't be able to do that. But in enormous foresight, Andreas Wolf and Olda already initiated a project a couple of years ago, together with the group of Christian Enz here at the university. And this is currently led by Lisa Gama in our group. That is a pixel detector where each pixel is mass sensitive. Each pixel is a little magnetic calorimeter, so it detects how much heat is deposited there. And these detectors have been used for X-rays, which is the similar energy range, but not for solid particles. But the test setup has shown that you can actually identify fragments from these large molecules very nicely. And this is the current setup that is being produced for the CSR. The problem is that with these detectors, you have to go to even lower temperatures, to millikelvin or something like that. And our 4 Kelvin environment is way too hot. So you have to shield this detector from the heat radiation from the 4 Kelvin. So this is currently underway, and we hope that with this, we will be able to answer that riddle and go to more complex molecule. Okay, now to the final part of my talk. There's another class of reactions that we want to look at. If you look at the sensitivity studies that check which are the most important or the most problematic reactions in interstellar environment, in protoplanetary disk, you find these electron recombination here, like H3O+, but you also find reactions with neutral atoms. And the reason for that is that neutral atoms in interstellar space, they exist, but here on Earth, you don't get them for free, because if you buy carbon, you don't get an atom, you get a piece of graphite, or you get a diamond or something. And if you buy O2, you get an O2 molecule, but you don't get an O2 atom. So to do these reactions like they happen in interstellar space, you have to not only produce cold molecular ions, you have to produce also ground state atoms. And if you look at most influential reactions in interstellar clouds, you get similar candidates, So we want to study reactions of cold molecular ions with neutral atoms in their ground state. So how do you do that? So essentially, we want to use our storage ring to store the molecular ions. So we take one ion source, inject it into the storage ring, and wait a little bit. And then we make a negative beam of the atom that we want, a negative carbon beam, for example, and shoot it towards the storage ring, but we dump it before it reaches the storage ring. And here we have a very strong laser. It's essentially a diode matrix of 500 individual lasers that we superimpose at a small angle, and that shoots away the extra electron at a few %. And then we have a neutral beam that flies just ballistically. It's not impressed by the fields anymore, and it flies ballistically for about 20 meters. And here inside the storage ring, it's superimposed to the ions, and the reaction, like this one, can go forward. So again, my little cartoon looks very simple. In reality, the technical realization was very hard, and this was done by Florian Krisse, a postdoc in my group, because to have a neutral beam at that high velocity and fly for 20 meters is actually quite tricky without spoiling the perfect vacuum inside the ring. So we were not allowed to lose any of the neutrals inside the storage ring. And also the density of the neutral beam is what you would call a perfect vacuum here on Earth, but we call it a beam because a fast beam has a very low density. So this was, was on the to-do list for many storage rings in the past, but it was actually never realized. And we were the first ones to get this working. And the first reaction we looked at was D2+ with carbon. And we did that for a reason. D2+ had been measured before, twice, and it doesn't cool at all. It has no dipole moment. So we can compare it to these measurements that were done at room temperature. And this is a comparison to a measurement that was done in New York in 2020. You can see it doesn't fit too badly. And this we used to benchmark our setup because it had never been done before. And now we know we can measure that also on an absolute scale. And in this measurement, they also measured H2+, and it looked identical. And from that, they inferred that there's no isotope effect. There should be no isotope effect. And they also found that the overall cross-section was about a factor of 3 lower than what was proposed by capture models. So we decided to go for HD+, for a molecule that has 2 different isotopes. And the prediction was that we shouldn't see any difference. And when we looked at the one channel, you get 2 different channels now. If you go for HD+ plus carbon, you get CD+. It looks similar, but it actually switches off earlier, which is weird already. And if you then go to CH plus, the other channel, you see there's a very strong isotope effect. And that CH plus actually switches off much later. So this was completely unexpected. But it gets even better because if you now take these rate coefficients and turn them into cross sections, and you compare them to the capture models, this is work done by Fabrice Daillou at the Paris Observatory, they actually match perfectly. There are two different theories here, one with some quasi-bound states that may or may not survive, and our measurements lie perfectly in the middle of them. So this factor of 3 capture cross-section difference, it goes away if you go to the lowest rotational states, because you have to know what states are involved. And the isotope effect that was initially predicted to be 0, if you go to the lowest states, it's perfectly reproduced. These are the theory measurements. It predicts an isotope effect of 1.6 in favor of CH+, and that goes up at higher energies, and that's exactly what we see. So once we're actually at the low temperature, we can understand this reaction. We've moved on to the more important H3++ carbon, and we also see that this is higher than the room temperature measurements, but the data are not of the quality yet, so I'm going to make them go away quickly. Then we moved on to protonated triatomic hydrogen, so to deuterated. So this would be what brings deuterium into the interstellar networks. And we can see all the different channels now. We can see CH+, we can see CD+, CH2+, and CHD+. These are currently under analysis, but these data are all good, so those will come out quickly. Yeah. Okay, so with this, I hope, okay, this is almost on time. So let me sum up. I hope I could convince you that this transition from magnetic storage rings to electrostatic storage rings for molecular physics was useful because it's actually pursued around the world. There are a number of electrostatic storage rings now, but this is by far the largest one. Our storage ring is now working quite well. We have done electron recombination measurements with a whole bunch of different molecular ions that are currently being analyzed. And we've also studied quite a bunch of design neutral collisions. I also wanted to show, I'm not going to explain this. We have a scientific program that is not related to astrophysics. I apologize in this to this audience, but it turns out that it sometimes in the end, when you analyze it, gets related to astrophysics. So this is the cooling of small isolated clusters. And it turns out that what dominates the cooling, which would be very similar to an isolated molecule that gets hit by a big photon in interstellar space, that cooling is dominated by the flux of the internal energy inside the molecule. And we can show and reproduce it and show that it's a power law dependence that we can follow over long, long times. Okay, with this, I want to conclude. I want to thank all the people that were involved. So I have a group that is mainly concerned with astrophysics. These people here, we work in the department of Klaus Blaum, and Andreas Wolf was the lead scientist for the CSR throughout its development. Ola Novotny is our electron recombination expert. Manfred Friese is our storage ring expert. And we have a number of international collaborations in Belgium, Xavier Aubin and Daniel Seven, and also here in Germany. And the Weizmann Institute in Israel has been a very long-term collaborator. Okay, with this, I want to thank you for having me here today. And I want to give the words to Richard. If you have any questions, just let me know. Let me know.
Thank you very much, Holger. I mean, looks very exciting. The fruits of this great journey you've been on, and you're doing ever more experiments. And this is clearly going to be essential for understanding precision, what's going on in the stellar medium. I'm sure there will be some questions. I'd like to ask the first one from Kees Dullemont.
Wow, this is just really amazing. I was completely flabbergasted. So I was just wondering, is maybe a little bit of a generic question that I have, is that there are these databases of chemical reaction coefficients that people like me and like others in the theorists in the community use to do our models. There are quite a number of reaction rates in there. Now, my question is, how much of these databases can we still trust? Is it at all possible to go along all these reaction rates, which is presumably just too much to do in the experiments? And so the final question, which actually connects these two, is: do you or are you able to find a deeper kind of physics from your experiments by which one could kind of fine tune the calculations that people are making so that you don't have to kind of measure all these reactions one by one.
Yeah, I think that's a very, very good question, because our experiments indeed take a long time. I'll try to find an extra slide here. So the databases, you're right, they have a lot of numbers in there. Most of those numbers are guessed. And those that have been measured have usually been measured at room temperature, and whether they're reliable or not is unclear. So what we try to do is we try to focus on the most important reactions, right? So that's why these sensitivity studies are very valuable for us, because it takes quite some time to measure and analyze. But it's true that all of this is useless if you don't eventually find an underlying principle. Oh, here we go. So this here is again showing this electron recombination of helium H+ as a function of, the rotational state, as a function of energy. As you can see, in the past, there was not, to my knowledge, although the theoreticians don't like that, there was not a single molecule for which the predictions could actually match the experiment. And now that we actually measure it state specifically and give the theoretician those data, something is very slow. Oh, oh, okay. Maybe I'll use this thing. So I just want to show you. Oh. I want to go to this one. It doesn't seem to do it. So it turns out, if Richard manages to show the other, there we go. Actually see that it now works, right? So if you go, this is a paper from 2 years ago, where the theoreticians were able to really match, for the first time, to my mind, such a diatomic molecule perfectly. And we're working on a similar scheme now for H2D+ with theoreticians, and we hope, because it's true, if we cannot measure all of these reactions, at some point we have to gain an understanding of this. And for the ion neutral reactions, most reaction rate coefficients in the databases are just from classical capture theory, the Lange rate coefficient or something like that. And it turns out, for the last reactions, sometimes I'm afraid to admit that most of the reactions, when you get really cold, they seem to resemble that quite well, actually. So maybe this principle is not so bad, but you have to prove it. And that's what we're working on right now. If you look at the databases, indeed, for example, when we started, there were about 100 reactions with neutral carbon atoms, and they were all just guessed with the same rate coefficient. They had not a single experimental value in there, and this is just a bad situation. I don't think we have to measure all of those, but if we find a pattern, then you at least are on surer footing. And if you take the important ones and measure those, I don't think we can measure all of those, but we have to find principles and put the important ones on a safer ground. And that's the idea.
Okay, thank you. Any more questions from the hall? Yeah, from the front here, please.
Thank you. You showed the lifetime of this very heavy silver dimer. Was it silver?
Silver, yeah.
And that was extremely large, close to a fraction of an hour. On the other hand, for the small molecules, the lifetime seems to be only a few seconds or even shorter than a second. So how is that correlated, the lifetime, with the mass?
So it's not that much shorter for the small molecules. Where did you take the second?
Well, it was on your slide. The storage time.
Yeah. A second? No, sometimes we just look at 1 second.
Yeah.
But so
there's no correlation.
No, there is a correlation
between the mass and
no, there is a correlation. There is a correlation.
How does it look like?
Yeah, the heavier molecules, they do have a longer lifetime, but
why is that?
Yeah, so we believe that the lifetime. So in honesty, we do not understand exactly what determines our lifetime, because it's not the vacuum anymore. The vacuum, if you extrapolate the density inside the storage ring, should allow for such a big molecule lifetimes on the order of 2 days. But what we see is typically, we have seen lifetimes now in the order of a few, like 2 hours or so, but the smaller molecules are more on the order of 10 minutes or something like this. And we believe what you can see, we have other diagnostics, we can see how the momentum spread of the particles in the storage ring evolves, and that momentum spread keeps growing. And we believe that the reason is that, unlike in a magnetic storage ring, magnetic fields can never accelerate particles if they're static, right? Electrostatic fields can accelerate particles. So if we have a little wiggle on our electrostatic electrodes and the molecule happens to fly through there at an inopportune moment, we can actually accelerate it a little bit. And that spreads out the momentum spread until at some point, very slowly, they leave the acceptance of the storage ring. We can, so this is our theory, at least, we see this momentum spread and we can make it much worse. If we put a tiny, like a millivolt wiggle on one of our high voltage electrodes, the beam gets destroyed very quickly. So we've actually upgraded our power supplies and that improves the situation. Now we can get even better lifetimes. And we believe that that is essentially what limits our lifetimes. For example, we can also see that if we can use electron cooling to work against that momentum spread, and then the lifetimes get longer again. So it's no longer the vacuum. It's the fact that particles in an electrostatic field can actually get accelerated. And then you depend on the stability of your power supplies, which already is very, very good. That's why we can store for such a long time, but it's no longer something that can be neglected. And the smaller molecules react more because you accelerate them more in the same kind of field, you know.
Okay, thank you. I just wanted to invite the Zoom audience too. If you have any questions, please just type you want to give a question in the chat, and then we'll bring you in to the discussion here acoustically. Any more questions from the audience here? I don't see anything. I wanted to ask you actually this question of the clusters at the end. I mean, what is the limitation to how heavy a cluster? I mean, obviously you've got to have a good charge. You've got to calibrate the charges on those things to get that known what you actually have. Obviously, I'm thinking of the transition to grains, at least to try and make the first steps there.
So from what I've learned from astronomical papers, any molecule with more than 4 atoms is a dust grain, right?
Well, okay.
No?
Yeah, I mean, I think when all the internal modes start to get mixed up and it becomes a continuum, but I mean, I think there's experts here who will be able to comment better on that.
To answer your question, I think, so there are different limits that we have. The storage ring itself on the fields doesn't have a nominal limit. We could store very heavy particles, but first we have to accelerate them and guide them to the storage rings. And there, for mass selection, we still have magnets. And I believe presently we're limited to about 1,000 mass units. We've stored particles with a few hundred mass units.
Yeah.
You know, so something like C60 would be currently still possible.
Yeah.
If we wanted to go even heavier, we would have to upgrade our. I mean, the magnets are not ideal anyway. We would have to use electrostatic deflection. The storage ring itself shouldn't have a problem with that. But some of the measurements become harder then, you know, because the particles become slower and slower. For example, electron cooling, to match the velocity of the particles, the electrons would have to come too slow. So there we believe that the limit is about mass 160, which would be good enough for these PAHs still, for the naphthalenes at least, which would be good enough for methanol and things like that.
Yeah.
The heavier ones like C60, we could still expose to electrons, but we couldn't easily cool them.
Right.
You know? Also, the cooling times would get too long.
I mean, one of the most important things will be the photoelectric efficiency in the yields when you have the photon interaction with these things. Do you see any prospect for doing that sort of measurement too?
Yes, actually, that's another thing I don't know if I'm going to dare to try to have a next slide.
I think it's just got so slow now. It just staggered to the end.
I think it doesn't want anymore. Tired. But yes, so actually the last slide that I showed and I couldn't explain is actually photo detachment of a small metal cluster that we use as a model system. And there we can see that it cools very, very slowly. And what we're doing right now, actually, the storage ring is open right now because the other department in our institute, Thomas Pfeiffer's department, puts in what's called a reaction microscope. And that is essentially a spectrometer that can measure if you expose something, if you fragment an ion, you can with photons or with a collision, you can measure all the fragments. You can measure the electrons as well as the fragments.
Okay.
And the electron energy can also be measured.
Yeah.
So then we can actually measure, you know, depending on the photon flux, how much electrons and what kind of energy the electrons.
I mean, that would be, you know, for the thermodynamics of this diffuse mode, it is so critical.
So we're aware of that.
Yeah.
And this is the next upgrade that's currently underway. We hope it's always, everything takes longer than you think, but we hope that it's going to be done at the beginning of next year.
Fantastic.
This spring, yeah.
Great, thank you. With that, let us now thank Holger again for this eye-opening look into what's possible in the laboratory now and in the future, and it's no doubt going to be very, very important for all of us observational astronomers. Thank you so much.